and now we are on to classification. So essentially, classification is differentiating between, data points and separating them into classes. So rather than predicting a numeric value, which we did with regression earlier, so linear regression and, the percentage survival chance, which is a numeric value, we actually want to predict classes. So what we're going to end up doing is predicting the probability that a specific data point or a specific entry or whatever we're going to call it is within all of the different classes it could be. So for the example here, we're going to use flowers. So it's called the iris, I think it's the iris flower dataset or something like that. And we're going to use some different properties of flowers to predict what species of flower it is. So that's the difference between classification and regression. Now, I'm not going to talk about the specific algorithm we're going to use here for classification because there's just so many different ones you can use. But yeah, I mean, if you really care about how they work on a lower mathematical level, I'm not going to be explaining that because it doesn't make sense to explain it for one algorithm when there's like hundreds and they all work a little bit differently. So you guys can kind of look that up and I'll tell you some resources and where you can find that. I'm also going to go faster through this example just because I've already covered kind of a lot of the fundamental stuff in linear regression. So hopefully we should get this one done a little bit quicker and move on to the next kind of aspects in this series. All right, so first steps, load TensorFlow, import TensorFlow. We've done that already. Dataset, we need to talk about this. So the dataset we're using is that iris flowers dataset like I talked about. And this specific dataset separates flowers into 3 different species. So we have these different species. This is the information we have. So septal length, petal width. We're going to use that information obviously to make the predictions. So given this information, in our final model, can it tell us which one of these flowers it's most likely to be? Okay, so what we're going to do now is define the CSV column names and the species. So the column names are just going to define what we're going to have in our data set as like the headers for the columns. Species obviously is just the species and we'll throw them there. All right, so now we're going to load in our data sets. So this is going to be different every time you're kind of working with models depending on where you're getting your data from. In our example, we're going to get it from Keras, which is kind of in sub-module of TensorFlow. It has a lot of useful data sets and tools that we'll be using throughout this series. But keras.utils.getFile, again, don't really focus on this. Just understand what this is going to do is save this file onto our computer as iristraining.csv, grab it from this link, and then what we're going to do down here is load the train and test, and again, notice this is training and this is testing, into 2 separate data frames. So here we're going to use the names of the columns as the CSV column names. We're going to use the path as whatever we loaded here. Header equals 0, which just means row 0 is the header. All right. So now we will move down and we'll have a look at our data set. So like we've done before. Oh, I've got to run this code first. CSV column names. Okay, so we're just running things in the wrong order here apparently. Okay, so let's look at the head. So we can see this is kind of what our data frame looks like. And notice that our species here are actually defined numerically. So rather than before, when we had to do that thing where, we made those feature columns and we converted the categorical data into numeric data with those kind of weird TensorFlow tools, this is actually already encoded for us. Now 0 stands for setosa, and then 1 and 2 obviously stand for these ones respectively. And that's how that works. Now these, I believe, are in centimeters, the septal length, petal width. That's not super important, but sometimes you do want to know that information. Okay. So now we're going to pop off those columns for the species like we did before and separate that into train Y, test Y, and then have a look at the head again. So let's do that and run this. Notice that is gone. Again, we've talked about how that works. And then these, if we wanted to have a look at them and actually, let's do this by just having a new block. Let's say train underscore Y dot, dot head. If I could spell head correctly. Okay, so we run head. And we can see this is what it looks like, nothing special. That's what we're getting. All right, so let's delete that. Let's look at the shape of our training data. I mean, we can probably guess what it is already, right? We're going to have shape 4 because we have 4 features. And then how many entries do we have? Well, I'm sure this will tell us. So 120 entries in shape 4. Awesome, that's our shape. Okay, input function. So we're moving fast here already. We're getting into a lot of the coding. So what I'm actually going to do is, again, copy this over into a separate document, and I'll be back in a second with all that. Okay, so input function time. We already know what the input function does because we used it previously. Now, this input function is a little bit different than before just because we're kind of changing things slightly. So here, we don't actually have any, We don't have any epochs, and our batch size is different. So what we've done here is rather than actually, defining like make input function, we just have input function like this. And what we're going to do is a little bit different when we pass this input function. I'll kind of show you. It's a little bit more complicated, but you can see that we've cleaned this up a little bit. So exactly, we're doing what we do before. We're converting this data, which is our features, which we're passing in here, into a data set, and then we're passing those labels as well. And then if we're training, so if training is true, what we're going to do is say dataset is equal to the dataset.shuffle. So we're going to shuffle that information and then repeat that. And that is all we really need to do. We can do dataset.batch at the batch size 256, return that, and we're good to go. So this is our input function. Again, these are kind of complicated. You kind of have to just get experience seeing a bunch of different ones to understand how to actually make one on your own. For now on, don't worry about it too much. You can pretty much just copy the input functions you've created before and modify them very slightly if you're going to be doing your own models. But by the end of this, you should have a good idea of how these input functions work. We will have seen like 4 or 5 different ones, and then, you know, we can kind of mess with them and tweak them as we go on, but don't focus on it too much. Okay, so input function. This is our input function. I'm not really going to go in too much more detail with that. And now our feature columns. So this is, again, pretty straightforward for the feature columns. All we need to do for this is, since they're all numeric feature columns, is rather than having 2 for loops where we were separating the numeric and categorical feature columns before, we can just loop through all of the keys in our training data set, and then we can append to my feature columns blank list, the feature column .numeric column, and the key is equal to whatever key we've looped through here. Now I'm going to show you what this means in case anyone's confused. Again, you can see when I print my feature columns, we get key equals septal length, we get our shape, and we get all of that other nice information. So let's copy this into the other one and have a look at our output after this. Okay, so my feature columns for key and train.keys. So notice train is here. Train.keys, what that does is actually give us all of the columns. So this was a really quick and easy way to kind of loop through all the different columns, although I could have looped through CSV column names and just removed the species column to do that, but again, we don't really need to. So for key and train.keys, my feature columns.append tf feature column numeric column key equals key. This was just going to create those feature columns. We don't need to do that vocabulary thing and that .unique because, again, these are all already encoded for us. Okay, awesome. So that was the next step. So let's go back here. Building the model. Okay, so this is where we need to talk a bit more in depth of what we're actually going to build. So the model for this is a classification model. Now there is like hundreds of different classification models we can use that are pre-made in TensorFlow. And so far what we've done with that linear classifier is that's a pre-made model that we kind of just feed a little bit of information to and it just works for us. Now here we have 2 kind of main choices that we can use for this kind of classification task that are pre-built in TensorFlow. We have a DNN classifier, which stands for a deep neural network, which we've talked about very vaguely, very briefly, and we have a linear classifier. Now, a linear classifier works very similarly to linear regression, except it does classification rather than regression, so we get actually numeric value, or we get, the labels, like probability of being a specific label rather than a numeric value. But in this instance, we're actually going to go with deep neural network. Now, that's simply because TensorFlow on their website, like all of this is kind of building off of TensorFlow website, just all of the code is very similar, and I've just added my own spin and explained things very in depth. They recommend using that. Deep neural network for this is a better kind of choice, but typically when you're creating machine learning apps, you'll mess around with different models and kind of tweak them, and you'll notice that it's not that difficult to change models because most of the work comes from loading and kind of pre-processing our data. Okay, so what we need to do is build a deep neural network with two hidden layers with 30 nodes and 10 hidden nodes each. Now, I'm going to draw out the architecture of this neural network in just 1 second, but I want to show you what we've done here. So we said classifier equals tf.estimator. So this estimator module just stores a bunch of pre-made models from TensorFlow. So in this case, DNN classifier is one of those. What we need to do is pass our feature columns just like we did to our linear classifier. And now we need to define the hidden units. Now, hidden units is essentially us building the architecture of the neural network. So like you saw before, we had an input layer, we had some like middle layers called our hidden layers in a neural network, and then we had our output layer. I'm going to explain neural networks in the next module, so this will all kind of click and make sense. For now, we've arbitrarily decided 30 nodes in the first hidden layer, 10 in the second, and the number of classes is going to be 3. Now that's something that we need to decide. We know there's 3 classes for the flowers, so that's what we've defined. Okay, so let's copy this in, go back to the other page here, and that is now our model. And now it is time to talk about how we can actually train the model, which is coming down here. Okay, so I'm going to copy this, I'm going to paste it over here, and let's just dig through this because this is a bit more of a complicated piece of code than we usually used to working with. I'm also going to remove these comments just to clean things up in here. So we've defined the classifier, which is a deep neural network classifier. We have our feature columns, hidden units, classes. Now to train the classifier. So we have this input function here. This input function is different than the one we created previously. Remember when the one we had previously was like make input, whatever function, I won't continue typing, and inside it defined another function, and it actually returned that function from this function. I know, complicated. If you're not a Python kind of pro, I don't expect that to make perfect sense. But here we just have a function, right? We do not returning a function from another function, it's just one function. So when we want to use this to train our model, what we do is create something called a lambda. Now a lambda is an anonymous function that can be defined in one line. When you write lambda, what that means is essentially this is a function. So this is a function, and whatever's after the colon is what this function does. Now this is a one-line function. So like if I create a lambda here, right? And I say lambda print hi, and I said x equals lambda, and I called x like that, this works. This is a valid line of syntax. And actually, I want to make sure that I'm not just like messing with you when I say that, and that this is actually correct. Okay, so sorry, I just accidentally trained the model, so I just commented that out. You can see we're printing hi, right? At the bottom of the screen, I know it's kind of small, but it does say hi. That's how this works, okay? So this is a cool thing. If you haven't seen this in Python before, that's what a lambda does. Allows you to define a function in one line. Now, the thing that's great about this is that we can say, like, you know, x equals lambda, and here put another function, which is exactly what we've done with this print function. And that means when we call x, it will, you know, execute this function, which will just execute the other function. So it's kind of like a chain, right? You call x is a function, and inside that function, it does another function, right? It's just like calling a function from inside a function. So what is lambda doing here? Well, since we need the actual function object, what we do is we define a function that returns to us a function. So this actually just like it calls this function when you put this here. Now there's no, it's very difficult to explain this if you don't really understand the concept of lambdas and you don't understand the input functions, but just know we're doing this because of the fact that we didn't embed another function and return the function object. If we had done that, you know, input function that we had created before where we had the interior function, then we wouldn't need to do this, because what would happen is we would return the input function, right? Like that, which means when we passed it into here, it could just call that directly. It didn't need to have a lambda. Whereas here though, since we need to just put a lambda, we need to define what this is, and then this works. That's just, there's no other way to really explain this. So yeah, what we do is we create this input function. So we have train y, and we have training equals true. And then we do steps equals 5,000. So this is similar to an epoch, except this is just defining a set amount of steps we're going to go through. So rather than saying like we'll go through the data set 10 times, we're just going to say we'll go through the data set until we've hit 5,000 numbers, like 5,000 things that have been looked at. So that's what this does with that train. Now let's run this and just look at the training output from our model. It gives us some like things here. We can kind of see how this is working. Notice that if I can stop here for a second, it tells us the current step. It tells us the loss, the lower this number, the better. And then it tells us global steps per second. So how many steps we're completing per second. Now at the end here, we get final step loss of 39, which is pretty high, which means this is pretty bad, but that's fine. This is kind of just our first test at training a neural network. So this is just giving us output while it's training to kind of say what's happening. Now, in our case, we don't really care because this is a very small model. When you're training models that are massive and take terabytes of data, you kind of care about the progress of them. So that's when you would use kind of that output, right? And you would actually look at that. Okay, so now that we've trained the model, let's actually do an evaluation on the model. So we're just going to say classifier.evaluate. And what we're going to do is a very similar thing to what we've done here, is just pass this input function, right? Like here with a lambda once again, and reason we add the lambda when we don't have this like double function going on, like a nested function. We need the lambda. And then in here, what we do is rather than passing train and train y, we're going to pass test, I believe. And then I think I just called it test y. Okay. And then for training, obviously this is false. So we can just set that false like that. I'm just going to look at the other screen to make sure I didn't mess this up because, again, I don't remember the syntax. Yeah, so classifier.evaluate test y looks good to me. We'll take this print statement just so we get a nice output for our accuracy. Okay, so let's look at this. Again, we're going to have to wait for this to train, but I will show you a way that we don't need to wait for this to train every time in 1 second, and I'll be right back. Okay, so what I'm actually going to do, and I've just kind of paused like the execution of this code, is throw this in the next block under, because the nice thing about Google Collaboratory is that I can run this block of code, right? I can train all this stuff, which is what I'll run now while we're talking, just so it happens. And then I can have another code block kind of below it, which I have here. And it doesn't matter, I don't need to rerun that block every time I change something here. So if I change something in any lower blocks, I don't need to change the upper block, which means I don't need to wait for this to train every time I want to do an evaluation on it. Anyways, so we've done this, we've got test, we got test y. I just need to change this instead of eval result. Actually, I need to say eval underscore result equals classifier.evaluate so that we can actually store this somewhere and get the answer. And now we'll print this, and notice this happens much, much faster. We get a test accuracy of 80%. So if I were to retrain the model, chances are this accuracy would change, again, because of the order in which we're seeing different flowers. But this is pretty decent considering we don't have that much test data, and we don't really know what we're doing, right? We're kind of just messing around and experimenting for right now. So to get 80% is pretty good. Okay, so actually, what am I doing? We need to go back now and do predictions. So how am I going to predict this for specific flowers? So let's go back to our core learning algorithms, and let's go to predictions. Now, I've written a script already just to save a bit of time that allows us to do a prediction on any given flower. So what I'm going to do is create a new block down here, code block, and copy this function in. Now we're going to digest this and kind of go through this on our own to make sure this makes sense. But what this little script does is allow the user to type in some numbers, so the septal length, width, and I guess petal length and width, and then it will spit out to you what the predicted class of that flower is. So we could do a prediction on every single one of our data points like we did previously, and we already know how to do that. I showed you that with linear regression. But here I just wanted to do it on one entry. So what do we do? So I start by creating an input function. It's very basic. We have batch size 256. All we do is we give some features, and we create a data set from those features that's a dict, and then .batch and the batch size. So what this is doing is, notice we don't give any y value, right? We don't give any labels. The reason we don't do that is because when we're making a prediction, we don't know the label, right? Like we actually want the model to give us the answer. So here I wrote down the features. I created a predict dictionary just because I'm going to add things to it. And then I just prompted here with a print statement, please type numeric values as prompted. So for feature and feature, valid equals true, while valid, val equals input feature colon. So this just means what we're going to do is for each feature, we're going to wait to get some valid response. Once we get some valid response, what we're going to do is add that to our dictionary. So we're going to say predict feature. So whatever that feature was, so septal length, septal width, petal length, or petal width is equal to a list that has, in this instance, whatever that value was. Now, the reason we need to do this is because, again, the predict method from TensorFlow works on predicting for multiple things, not just one value. So even if we only have one value we want to predict for, we need to put it inside of a list because it's expecting the fact that we will probably have more than one value every time I change something here. So eval, I print this, and notice this happens much, much faster. We get a test accuracy of 80%. So if I were to retrain the model, chances are this accuracy would change, again, because of the order in which we're seeing different flowers. But this is pretty decent considering we don't have that much test data, and we don't really know what we're doing, right? We're kind of just messing around and experimenting for right now. So to get 80% is pretty good. Okay, so actually, what am I doing? We need to go back now and do predictions. So how am I going to predict this for specific flowers? So let's go back to our core learning algorithms, and let's go to predictions. Now, I've written a script already just to save a bit of time that allows us to do a prediction on any given flower. So what I'm going to do is create a new block down here, code block, and copy this function in. Now we're going to digest this and kind of go through this on our own to make sure this makes sense. But what this little script does is allow the user to type in some numbers, so the septal length, width, and I guess petal length and width, and then it will spit out to you what the predicted class of that flower is. So we could do a prediction on every single one of our data points like we did previously, and we already know how to do that. I showed you that with linear regression. But here I just wanted to do it on one entry. So what do we do? So I start by creating an input function. It's very basic. We have batch size 256. All we do is we give some features, and we create a data set from those features that's a dict, and then .batch and the batch size. So what this is doing is, notice we don't give any y value, right? We don't give any labels. The reason we don't do that is because when we're making a prediction, we don't know the label, right? Like we actually want the model to give us the answer. So here I wrote down the features. I created a predict dictionary just because I'm going to add things to it. And then I just prompted here with a print statement, please type numeric values as prompted. So for feature and feature, valid equals true, while valid, val equals input feature colon. So this just means what we're going to do is for each feature, we're going to wait to get some valid response. Once we get some valid response, what we're going to do is add that to our dictionary. So we're going to say predict feature. So whatever that feature was, so septal length, septal width, petal length, or petal width is equal to a list that has, in this instance, whatever that value was. Now, the reason we need to do this is because, again, the predict method from TensorFlow works on predicting for multiple things, not just one value. So even if we only have one value we want to predict for it, we need to put it inside of a list because it's expecting the fact that we will probably have more than one value in which we would have multiple values in the list, right? Each representing a different row or a new flower to make a prediction for. Okay. Now we say predictions equals classifier.predict, and then in this case we have input function lambda input function predict, which is this input function up here. And then we say for prediction dictionaries, because remember every prediction comes back as a dictionary. In predictions, we'll say the class ID is equal to whatever the class IDs of the prediction dictionary at 0, and these are simply what I don't know exactly how to explain this. We'll look at it in a second, and I'll go through that. And then we have the probability is equal to the prediction dictionary probabilities of class ID. Okay. Then we're going to say print prediction is. We're going to do this weird format thing. I just stole this from TensorFlow. And it's going to be the species at the class ID and then 100 times probability, which will give us actual integer value. We're going to digest this, but let's run this right now and have a look. So please type numeric values as prompted. Septal length, let's type like 2.4. Septal width 2.6, petal width, let's just say that's like 6.5, and yeah, petal width like 6.3. Okay, so then it calls this and it says prediction is Virginica. I guess that's the class we're going with, and it says that's an 86.3% chance that that is the prediction. So yeah, that is how that works. So that's what this does. I wanted to give a little script. I wrote most of this. I mean, I stole some of this from TensorFlow, but just to show you how we can actually predict on one value. So let's look at these prediction dictionary because I just want to show you what one of them actually is. So I'm going to say print pred underscore dict, and then this will allow me to actually walk through what class IDs are, probabilities are, and how I've kind of done this. So let's run this septal length. Okay, let's just go like 1.4, 2.3. I don't know what these values are going to end up being, and we get prediction is same one with 77.1%, which makes sense because these values were similar, kind of in difference to what I did before. Okay, so this is the dictionary. So let's look for what we were looking for. So probabilities, notice we get 3 probabilities, one for each of the different classes. So we can actually say what, the percentages for every single one of the predictions. Then what we have is class IDs. Now class IDs, what this does is tell us what class ID it predicts is actually the flower, right? So here it says 2, which means that this probability at 77%, that's at index 2 in this array, right? So that's why this value is 2. So it's saying that that class is 2. It thinks it's class 2. Like that's whatever was encoded in our system is 2, and that's how that works. So that's how I know which one to print out, is because this tells me it's class 2. And I know from making this list all the way back up here, if I can get rid of this output, where is it? When I say species, that number 2 is Virginica, or I guess that's how you say it. So that is what the classification is, or that's what the prediction is. So that's how I do that, and that's how that works. Okay, so I think that is pretty much it for actually classification. So that was pretty basic. I'm going to go and see if there's anything else that I did for classification in here. Okay, so here I just put some examples. So here's some example input and expected classes. So you guys could try to do these if you want. So for example, this one, septal length, septal width. So for 5.1, 3.3, 1.7, and 0.5, the output should be setosa. For 5.9, 3.0, 4.2, 1.5, it should be this one. And then obviously this for this. Just so you guys can mess with them if you want. But that's pretty much it for classification. And now on to clustering. Okay, so now we're moving on to clustering. Now, clustering is the first unsupervised learning algorithm that we're going to see in this series, and it's very powerful. Now, clustering only works for a very specific set of problems, and you use clustering when you have a bunch of input information or features, but you don't have any labels or output information. Essentially, what clustering does is finds clusters of like data points and tells you the location of those clusters. So you give a bunch of training data, you can pick how many clusters you want to find. So maybe we're going to be classifying digits, right? Handwritten digits using k-means clustering. In that instance, we would have 10 different clusters for the digits 0 through 9, and you pass all this information, and the algorithm actually finds those clusters in the data set for you. We're going to walk through an example that'll make sense, but I just want to quickly explain the basic algorithm behind k-means. It's essentially the set of steps, because I'm going to walk you through them and with a visual example. So we're going to start by randomly picking k points to place k centroids. Now, a centroid stands for where our current cluster is kind of defined, and we'll see it in a second. The next step is we're going to assign all of the data points to the centroids by distance. So actually, now that I'm talking about this, I think it just makes more sense to get right into the example, because if I keep talking about this, you guys are probably just going to be confused, although I might come back to this just to reference those points. Okay, so let's create a little graph like this in 2 dimensions for our basic example, and let's make some data points here. So I'm just going to make them all red, and you're going to notice that I'm going to make this kind of easier for ourselves by putting them in like their own unique little groups, right? So actually, we'll add one up here. Then we can add some down here and down here. Now, the algorithm starts for k-means clustering, and you guys will understand how this works as we continue, by randomly picking k centroids. Now, I'm going to denote a centroid by a little filled in triangle like this. And essentially what these are is where these different clusters currently exist. So we start by randomly picking k, which is what we've defined. So like me in this instance, we're going to say k equals 3. K centroids wherever. So maybe we put one, somewhere like here. And you know what? I might not bother filling these in because they're going to take a while. Maybe we put one here. And maybe we end up putting one over here. Now, I've kind of put them close to where clusters are, but these are going to be completely random. Now, what happens next is each group or each data point is assigned to a cluster by distance. So essentially what we do is for every single data point that we have, we find what's known as the Euclidean distance, or it actually could be a different distance. You could use like Manhattan distance, if you guys know what that is, to all of the centroids. So let's say we're looking at this data point here. What we do is find the distance to all of these different centroids. And we assign this data point to the closest centroid. So the closest one by distance. Now in this instance, it's looking like it's going to be a bit of a tie between this centroid and this centroid, but I'm going to give it to the one on the left. So what we do is we're going to say this is now a part of this centroid. So if I'm calling this, like, let's just say this is centroid 1, this is centroid 2, and this is centroid 3, then this now is going to be a part of centroid 1 because it's closest to centroid 1. And we can go through and we do this for every single data point. So obviously we know all of these are going to be our 1s, right? And we know these are going to be our 2, so 2, 2, 2. And then these are obviously going to be our 3. Now I'm actually just going to add a few other data points because I want to make this a little bit more sophisticated almost, if that makes any sense. So I'll add those data points here. We'll even add one here, and now we'll give these labels. So these ones are close, so I'm going to say this one's 1. I'm going to say this one's 2. I know it's not closest to it, but just because I want to do that for now. We'll say 2 for that, and we'll say 3 here. Okay, so now that we've done that, we've labeled all of these points. What we do is we now move these centroids that we've defined into the middle of all of their data points. So what I do is I essentially find, it's called center of mass, the center of mass between all of the data points that are labeled the same. So in this case, these will be all the ones that are labeled the same. And I take this centroid, which I'm going to have to erase, get rid of it here, and I put it right in the middle. So let's go back to blue, and let's say the middle of these data points ends up being somewhere around here. So we put it in here, and this is what we call center of mass, and this again would be centroid 2. So let's just erase this, and there we go. Now we do the same thing with the other centroids. So let's remove these ones, let's remove these ones. So for 3, I'm saying it's probably going to be somewhere in here. And then for 1, our center of mass is probably going to be located somewhere about here. Now what I do is I repeat the process that I just did, and I reassign all of the points now to the closest centroid. So all these points that are labeled 1, 2, all of that, you know, we can kind of remove their labels, and this is just going to be great, me trying to erase the labels. I shouldn't have wrote them on top, but essentially what we do is we're just going to be like reassigning them. So I'm going to say, okay, so this is 2, and we just do the same thing as before, find the closest distance. So we'll say, you know, these can stay in the same cluster. Maybe this one actually here gets changed to 1 now, because it's closest to centroid 1, and we just reassign all these points. And maybe, you know, this one now, if it was 2 before, let's say like this one's 1, and we just reassign them. Now we repeat this process of finding the closest, or assigning all of the points to their closest centroid, moving the centroid into the center of mass, and we keep doing this until eventually we reach a point where none of these points are changing which centroid they're a part of. So eventually we reach a point where I'm just going to erase this and draw like a new graph because it'll be a little bit cleaner. But what we have is, you know, like a bunch of data points. So we have some over here, some over here. Maybe we'll just put some here, and maybe we'll do like a k equals 4 example for this one. And we have all these centroids, and I'll just draw these centroids with blue again, that are directly in the middle of all of their data points. They're like as in the middle as they can get. None of our data points have moved, and we call this now our cluster. So now we have these clusters, we have these centroids, right? We know where they are. And what we do is when we have a new data point that we want to make a prediction for or figure out what cluster it's a part of, what we do is we will plot that data point. So let's say it's this new data point here. We find the distance to all of the clusters that exist, and then we assign it to the closest one. So obviously it would be assigned to that one. And we can do this for any data point, right? So even if I put a data point all the way over here, well, its closest cluster is this, so it gets assigned to this cluster, and my output will be whatever this label of this cluster is. And that's essentially how this works. So you're just clustering data points, figuring out which ones are similar, and this is a pretty basic algorithm. I mean, you draw your little triangle, you find the distance from every point to the triangle, or to all of the triangles actually, and then what you do is just simply assign those values to that centroid. You move that centroid to the center of mass, and you repeat this process constantly until eventually you get to a point where none of your data points are moving. That means you've found the best clusters that you can, essentially. Now, the only thing with this is you do need to know how many clusters you want for k-means clustering, because k is a variable that you need to define. Although there is some algorithms that can actually determine the best amount of clusters for a specific data set, but that's a little bit beyond what we're going to be focusing on right now. So that is pretty much clustering. There's not really much more to talk about it, especially because we can't really code anything for it now. So we're going to move on to hidden Markov models. Now, hidden Markov models are way different than what we've seen so far. We've been using kind of algorithms that rely on data. So like k-means clustering, we gave a lot of data and we clustered all those data points, found those centroids, used those centroids to find where new data points should be. Same thing with linear regression and classification. Whereas hidden Markov models, we actually deal with probability distributions. Now, the example we're going to go into here, and it's kind of, I have to do a lot of examples for this because it's a very abstract concept, is a basic weather model. So what we actually want to do is predict the weather on any given day, given the probability of different events occurring. So let's say we know, maybe in like a simulated environment or something like that, this might be an application, that we have some specific things about our environment. Like we know if it's sunny, there's an 80% chance that the next day it's going to be sunny again, and a 20% chance that it's going to rain. Maybe we know some information about sunny days and about cold days, and we also know some information about the average temperature on those days. Using this information, we can create a hidden Markov model that will allow us to make a prediction for the weather in future days, given kind of that probability that we've discovered. Now you might be like, well, how do we know this? Like, how do I know this probability? A lot of the times you actually do know the probability of certain events occurring or certain things happening, which makes these models really good. But there's some times where what you actually do is you have a huge data set and you calculate the probability of things occurring based on that data set. So we're not going to do that part because that's just kind of going a little bit too far, and the whole point of this is just to introduce you to some different models. But in this example, what we will do is use some predefined probability distributions. So let me just read out the exact definition of a hidden Markov model and we'll start going more in depth. So the hidden Markov model is a finite set of states, each of which is associated with a generally multidimensional probability distribution. Transitions among the states are governed by a set of probabilities called transition probabilities. So in a hidden Markov model, we have a bunch of states. Now, probability that we've discovered. Now you might be like, well, how do we know this? Like, how do I know this probability? A lot of the times you actually do know the probability of certain events occurring or certain things happening, which makes these models really good. But there's some times where what you actually do is you have a huge data set and you calculate the probability of things occurring based on that data set. So we're not going to do that part because that's just kind of going a little bit too far, and the whole point of this is just to introduce you to some different models. But in this example, what we will do is use some predefined probability distributions. So let me just read out the exact definition of a hidden Markov model and we'll start going more in depth. So the hidden Markov model is a finite set of states, each of which is associated with a generally multidimensional probability distribution. Transitions among the states are governed by a set of probabilities called transition probabilities. So in a hidden Markov model, we have a bunch of states. Now, in the example that I was just talking about with this weather model, the states we would have is hot day and cold day. Now, these are what we call hidden because never do we actually access or look at these states while we interact with the model. In fact, what we look at is something called observations. Now, at each state, we have an observation. I'll give you an example of an observation. If it is hot outside, Tim has an 80% chance of being happy. If it is cold outside, Tim has a 20% chance of being happy. That is an observation. So at that state, we can observe the probability of something happening during that state is X, right? Or is Y, or whatever it is. So we don't actually care about the states in particular, we care about the observations we get from that state. Now in our example, what we're actually going to do is we're going to look at the weather as an observation for the state. So for example, on a sunny day, the weather has, the probability of being between 5 and 15 degrees Celsius with an average temperature of 11 degrees. That's a probability we can use. Now I know this is slightly abstract, but I just want to talk about the data we're going to work with here. I'm going to draw out a little example, go through it, and then we'll actually get into the code. So let's start by discussing the type of data we're going to use. So typically in previous ones, right, we used like hundreds, if not like thousands of entries or rows or data points for our models to train. For this, we don't need any of that. In fact, all we need is just constant values for probability and transition distributions and observation distributions. Now what I'm going to do is go in here and talk about states, observations, and transitions. So we have a certain amount of states. Now we will define how many states we have, but we don't really care what that state is. So we could have states, for example, like warm, cold, high, low, red, green, blue. We can have as many states as we want. We could have one state, to be honest, although that would be kind of strange to have that. And these are called hidden because we don't directly observe them. Now, observations. So each state has a particular outcome or observation associated with it based on a probability distribution. So it could be the fact that during a hot day, it is 100% true that Tim is happy. Although, in a hot day, we could observe that 80% of the time Tim is happy and 20% of the time he is sad, right? Those are observations we make about each state. And each state will have their different observations and different probabilities of those observations occurring. So if we were just going to have like an outcome for the state, that means it's always the same. There's no probability that something happens. And in that case, that's just called an outcome because the probability of the event occurring will be 100%. Okay, then we have transitions. So each state will have a probability defining the likelihood of transitioning to a different state. So for example, if we have a hot day, there will be a percentage chance that the next day will be a cold day. And if we have a cold day, there will be a percentage chance that the next day is either a hot day or a cold day. So we're going to go through like the exact what we have for our specific model below. But just understand there's a probability that we could transition into a different state. And from each state, we can transition into every other state or a defined set of states given a certain probability. So I know it's a mouthful. I know it's a lot. But let's go into a basic drawing example because I just want to illustrate like graphically a little bit kind of how this works in case these ideas are a little bit too abstract for any of you. Okay, so I'm just pulling out the drawing tablet. Just 1 second here, and let's do this basic weather model. So what I'm going to do is just simply draw 2 states. Actually, let's do it with some colors because why not? So we're going to use yellow, and this is going to be our hot day, okay? This is going to be our sun. And then I'm just going to make a cloud. We'll just do like a gray cloud. This will be my cloud, and we'll just say it's going to be raining over here. Okay, so these are my 2 states. Now, in each state, there's a probability of transitioning to the other state. So for example, in a hot day, we have a, let's say, 20% chance of transitioning to a cold day. And we have a 80% chance of transitioning to another hot day, like the next day, right? Now, in a cold day, we have, let's say, a 30% chance of transitioning to a hot day. And we have, in this case, what is that going to be? A 70% chance of transitioning to another cold day. Now, on each of these days, we have a list of observations. So these are what we call states, right? So this could be S1 and this could be S2. It doesn't really matter like if we name them or anything. We have 2 states. That's what we know. We know the transition probability. That's what we've just defined. Now we want the observation probability or distribution for that. So essentially, on a hot day, our observation is going to be that the temperature could be between 15 and 25 degrees Celsius with an average temperature of, let's say, 20. So we could say observation, right? So say observation, and we'll say that the mean, so the average temperature is going to be 20, and then the distribution for that will be like the minimum value is going to be 15, and the max is going to be 25. So this is what we call actually like a standard deviation. I'm not really going to explain exactly what standard deviation is, although you can kind of think of it as something like this. So essentially there's a mean, which is the middle point, the most common event that could occur. And at different levels of standard deviation, which is going into statistics, which I don't really want to mention that much because I'm definitely not an expert, we have a probability of hitting different temperatures as we move to the left and right of this value. So on this curve somewhere, we have 15, and on this curve to the right somewhere, we have 25. Now we're just defining the fact that this is where we're going to kind of end our curve. So we're going to say that like the probability is in between these numbers. It's going to be in between 15 and 25 with an average of 20, and then our model will kind of figure out some things to do with that. That's as far as I really want to go in standard deviation, and I'm sure that's like a really horrible explanation, but that's kind of the best I'm going to give you guys for right now. Okay, so that's our observation here. Now our observation over here is going to be similar. So we're going to say mean on a cold day temperature is going to be 5 degrees. We'll say the minimum temperature maybe is going to be something like -5, and the max could be something like 15, or like, yeah, we can say 15. So we'll have some distribution. That's just what we want to understand, right? And this is kind of a strange distribution because we're dealing with standard deviation, although we can just deal with like straight percentage observations. So for example, there's a 20% chance that Tim is happy, or there's an 80% chance that he is sad. Like those are probabilities that we can have as our observation probabilities in the model. Okay, so that was a lot of lingo. There's a lot going on. We're going to get into like a concrete example now, so hopefully this should make more sense. But again, just understand states, transitions, observations. We don't actually ever look at the states. We just have to know how many, though, is what do we even do with this model? So like once I make this, right? Once I make this hidden Markov model, what's the point of it? Well, the point of it is to predict future events based on past events. So if we know that probability distribution, and I want to predict the weather for the next week, well, I can use that model to do that, because I can say, well, if the current day today is warm, then what is the likelihood that the next day tomorrow is going to be cold, right? And that's what we are kind of doing with this model. We're making predictions for the future based on probability of past events occurring. Okay. So imports and setup. So let's just run this. Oh, we already loaded. Import TensorFlow. And notice that here I've imported TensorFlow probability is TFP. This is because this is a separate module from TensorFlow that deals with probability. Now we also need TensorFlow 2, but for this hidden Markov model, we're going to use the TensorFlow probability module. Not a huge deal. Okay, so weather model. So this is just going to define what our model actually is, so the different parts of it. So this is taken directly from the documentation of TensorFlow. You guys can see, where I have all this information from, like I've sourced all of it. But essentially what the model we're going to try to create is that cold days are encoded by 0 and hot days are encoded by 1. The first day in our sequence has an 80% chance of being cold. So whatever day we're starting out at has an 80% chance of being cold, which would mean 20% chance of being warm. A cold day has a 30% chance of being followed by a hot day, and a hot day has a 20% chance of being followed by a cold day, which would mean, 70% cold to cold and 80% hot to hot. On each day, the temperature is normally distributed with mean and standard deviation 0 and 5 on a cold day, and mean and standard deviation 15 and 10 on a hot day. Now, what that means, standard deviation, is essentially, we can read this thing here, is that on a hot day, the average temperature is 15, that's mean, and ranges from 5 to 25 because the standard deviation is 10 of that, which just means 10 on each side, kind of the min-max value. Again, I'm not in statistics, so please don't quote me on any definitions of standard deviation. I'm just trying to explain it enough so that you guys can understand what we're doing here. Okay, so what we're going to do to model this, and I'm just kind of going through this fairly quickly because it's pretty easy to really do this, is I'm going to load the TensorFlow probability distributions kind of module and just save that as TFD. And I'm just going to do that so I don't need to write tfp.distributions. All of this. I can just kind of shortcut it. So you'll notice I'm referencing TFD here, which just stands for tfp.distributions, and TFP is TensorFlow probability. Okay, so my initial distribution is TensorFlow probability distributions.categorical. This is probability of 80% and 20%. Now this refers to point 2. So let's look at point 2. The first day in our sequence has an 80% chance of being cold. So we're saying that that's essentially what this is. The initial distribution of being cold is 80% and then 20% after. Categorical is just a way that we can do this distribution. Okay, so transition distribution. What is it? TensorFlow probability categorical. The probability is 70% and 30% and 20% and 80%. Now notice that since we have two states, we've defined two probabilities. Notice since we have two states, we have defined two probabilities, the probability of landing on each of these states at the very beginning of our sequence. This is the transition probability, referred to points 3 and 4 above. So this is what we have here. So cold day has 30% chance, 20% chance for a hot day, and that's what we've defined. So we say this is going to be cold day, state 1. We have 70% chance of being cold day again. We have 30% chance of going hot day, and then, reverse here. Okay, so observation distribution. Now, this one is a little bit different, but essentially we do tfd.normal, Now, I don't know, I'm not going to explain exactly what all of this is, but when you're doing standard deviation, you're going to do it like this, where you're going to say loc, which stands for your average or your mean, right? So that was our average temperature, is going to be 0 on a hot day, 15 on a cold day. The standard deviation on the cold day is 5, which means we range from -5 to 5 degrees. And on a hot day, it's 10. So that is going to be, we go range from 5 to 25 degrees, and our average temperature is 15. Now, the reason we've added dot here is because these just need to be float values. So rather than inserting integers here and having potentially type errors later on, we just have floats. Okay, so the loc argument represents the mean, and the scale is the standard deviation. Yeah, exactly what we just defined there. All right, so let's run this. I think we actually already did. And now we can create our model. So to create the model is pretty easy. I mean, all we do is say model equals TensorFlow distribution dot hidden Markov model. Give it the initial distribution, which is equal to initial distribution, transition distribution, observation distribution, and steps. Now, what is steps? Well, steps is how many days we want to predict for. So the number of steps is how many times we're going to step through this probability cycle and run the model, essentially. Now, remember, what we want to do is we want to predict the average temperature on each day, right? Like that's what the goal of our example is to predict the average temperature. So given this information, using these observations and using these transitions, what we'll do is predict that. So I'm going to run this model. What is the issue here? Tensor is unhashable if tensor is... Okay, give me 1 sec. I'll have a look here, although I haven't had this issue before. Okay, so after a painful amount of searching on Stack Overflow and Google and actually just reading through more documentation on TensorFlow, I have determined the issue. So remember the error was we were getting on actually this line here. I think I can see what the output is. Okay, well, this is a different error. But anyways, there was an error at this line. Essentially, what was happening is we have a mismatch between the two versions here. So the most recent version of TensorFlow is not compatible with the older version of TensorFlow probability, at least in the sense that the things that we're trying to do with it. So I just need to make sure that I installed the most recent version of TensorFlow probability. So what you need to do, if this is in your notebook, and this should actually work fine for you guys because this will be updated by the time you get there, but in case you run into the issue, I'll, deal with it. But essentially what you're going to do is select version 2.x of TensorFlow. You're going to run this install command. So you're going to install TensorFlow probability, just run this command. Then after you run this command, you're going to need to restart your runtime. So go to runtime and then restart runtime. And then you can just continue on with the script, select TensorFlow 2.x again, do your imports, and then, we'll test if this is actually going to work for us here. Run our distributions, create the model without any issues this time. Notice no red text, and then run this final line, which will give you the output. Now, this is what I wanted to talk about here that we didn't quite get to because we were having some bugs. But this is how we can actually kind of run our model and see the output. So what you can do is do model.mean. So you say mean equals model.mean. And what this is going to do is essentially just calculate the probability. It's going to essentially take that from the model. Now, when we have model.mean, this is what we call, a partially defined tensor. So remember our tensors were like partially defined computations? Well, that's what model.mean actually is. That's what this method is. So if we want to get the value of that, what we actually need to do is create a new session in TensorFlow, run this part of the graph, which we're going to get by doing mean.numpy, and then we can print that out. So I know this might seem a little bit confusing, but essentially to run a session in the new version of TensorFlow, so 2.x or 2.1 or whatever it is, you're going to type with tf.compat.v1.session as sesh. And then, this doesn't really matter what you have here, but whatever you want. And then what I'm doing is just printing mean.numpy. So to actually get the value from this here, this variable, I call .numpy. And then what it does is print out this array that gives me the expected temperatures on each day. So we have, 3, 6, essentially 7.5, 8.25. And you can see these are the temperatures based on the fact that we start with an initial probability of starting on a cold day. So we kind of get that here, right? We're starting at 3 degrees. That's what it's determined we're going to start at. And then we have all of these other temperatures that's predicting for the next days. Now notice if we recreate this model, so I'll just rerun the distributions, rerun them, and go model.mean again. This stays the same, right? Well, because our probabilities are the same, this model is going to do the calculation the exact same. There's not really any training that goes into this. So we get, very similar, if not the exact same values. I can't remember if these are identical, but that's what it looks like to me. We can run this again. See, we get the same one. And we'll create the model one more time. And let me just check these values here to make sure I'm not lying to you guys. Yes, they are the exact same. Okay, so let's start messing with a few probabilities and see what we can do to this temperature and see what changes we can cause. So if I do 0.5 here and I do 0.5 for the categorical probability, remember this refers to points 3 and 4 above. So that's a cold day has a 30% chance of being followed by a hot day, and then a hot day has a 20% chance of being followed by a cold day. So what I've just done now is change the probability to be 50%, so that a cold day now has a 50% chance of being followed by a hot day and a 50% chance of being followed by a cold day. And let's recreate this model. Let's rerun this and let's see if we get a difference. Oh, we do. Notice this. The temperature now is going a little bit higher. Now notice that we get the same starting temperature because that's just the average based on this probability that we have here. But if we wanted to potentially start, hotter, we could reverse these numbers. We go 0.2, 0.8. Let's rerun all of this. And now look at this, what our temperatures are. We start at 12 and then we actually drop our temperature down to 10. So that's how this hidden Markov model works. Now this is nice because you can just tweak the probabilities. This happens pretty well instantly, and we can have a look at our output very nicely. So obviously this is representing the temperature on our, the first day. This would be the second day, third day, fourth day, fifth, sixth, seventh. And obviously, the more days you go on, the least accurate this is probably going to be because it just runs off probability. And if you're going to try to predict, a year in advance and you're using the weather that you have from, I guess, the previous year, you're probably not going to get a very accurate prediction. But anyways, these are hidden Markov models. They're not extremely useful. There is some situations where you might want to use something like this. So that's why we're implementing them in this course and showing you how they work. It's also another feature of TensorFlow that a lot of people don't talk about or see. And, personally, I hadn't really heard of hidden Markov models until I started developing this course. So anyways, that has been it for this module. Now, I hope that this kind of gave you guys a little bit of an idea of how we can actually implement some of these machine learning algorithms, a little bit of an idea of how to work with data, how we can feed that to a model, the importance between testing and training data, and then obviously linear regression is one we focused a lot on, so I hope you guys are very comfortable with that algorithm. And then what was the second one we did? I gotta go up to remember exactly the sequence we had here. So classification, that one was important as well, so I hope you guys really understood that. Clustering, we didn't go too far into that, but again, this is an interesting algorithm, and if you need to do some kind of clustering, you now know of one algorithm to do that called k-means clustering, and you understand how that works, and now you know hidden Markov models. So in the next module, we're going to start covering neural networks. We now have the knowledge we need to really dive in there and start doing some cool stuff. And then in the future modules, we're going to do deep computer vision. I believe we're going to do chatbots with recurrent neural networks, and then some form of reinforcement learning at the end. So with that being said, let's go to the next module.